Part 2, Binary Compounds. So chemical nomenclature is the naming of chemical substances. And under the guise of inorganic nomenclature, there are ionic compounds and covalent compounds. And I'm going to address a little bit about the differences between ionic and covalent compounds. There are also is organic nomenclature, and that is a broad regime covering mostly compounds involving carbon and hydrogen. We'll touch on some of that in Chemistry 134, but this is primarily taught in organic chemistry. So let's begin with ionic bonds. Ionic bonds are associated with ionic compounds, and typically these are formed between metals and nonmetals. What you have is the metal gives up an electron and it gives it to a nonmetal. So the metal has a positive charge, the nonmetal has a negative charge, and it's the positive negative charge difference that keeps these together. These compounds typically form crystals. They're also usually soluble in water, and when they dissolve in water, they separate into their ions. Covalent compounds are typified by being molecules. So covalent compounds are generally formed between nonmetals. You can see a series of examples of nonmetals here, like hydrogen, oxygen, water. We've got carbon monoxide, carbon dioxide. So covalent systems exist as what are called molecular compounds. And the electrons are shared between the atoms, and it's the sharing that keeps these bound together. So when you have a covalent compound, you should think of individual molecules, and they can be in a gas phase, the liquid phase, or the solid phase. When you think of an ionic compound, typically you just think of a solid. It's usually a powder or a crystal, and really what you have are clumps of molecules that are arranged in such a way that the charge is neutral on these compounds. So the rules for nomenclature surround the idea that elements are going to have charge. And if we're talking about a cation, the cation is going to retain the name of the element. So for example, sodium with a plus charge on it is just going to be sodium. And we know it has a +1 charge because of where it's at on the periodic table. The anions get the suffix IDE. So if I take an oxygen and put a -2 on it, it's going to be called oxide. Oxygen typically has a -2 charge on it. So if I say oxide, you know oxygen with a -2. The resulting compound has no charge. So if I take, for example, sodium chloride, taking a sodium with a +1 charge, and I'm going to put a single chlorine on there because it has a single negative charge. The charges cancel. If I look at a different element like, let's say, sulfur, I'm going to need 2 sodiums to balance the sulfur. Notice the 2 subscript on the sodium indicating that there's 2 sodium atoms next to the sulfur, and that would be sodium sulfide. So our rules then for inorganic nomenclature: first, write the name of the cation. Then, if the anion is an element, change its ending to IDE. If it's an anion, is a polyatomic ion, you simply write the name of the polyatomic ion. And we'll talk about polyatomic ions in the next section. If the cation can have more than one possible charge, write the charge as a Roman numeral in parenthesis. We'll talk more about that later on as well. So inorganic nomenclature, we do not use prefixes. Prefixes are not used for common salts. So for example, Na2O is named sodium oxide, not disodium oxide, not disodium monoxide. Don't use Greek prefixes because we know what the charge is, and if we know what the charge is, we should be able to figure out what the formula is from that. So let's look at the periodic table showing trends for ionic charges. And we have main group elements on the left-hand side, which are just the alkali and earth alkali metals. We have main group elements on the right-hand side, which are halogens, oxides, and nitrides. And then we have a small cluster of metals in the middle. And these are important because they have a single charge in our ionic compounds. Aluminum and gallium always have a +3 charge. Zinc and cadmium always have a +2 charge. Silver always has a +1. What's important about that is later on we're going to talk about elements where you need to use Roman numerals because they can vary their charges. These elements, the 5 right there in the middle, retain that charge. So silver is always a +1, so we do not use Roman numerals in such case. Zinc and cadmium are always +2. Don't use Roman numerals to designate the charge on those metals. So you treat those just like they're earth, alkali, and alkali metals. So let's consider an example where I've just taken a alkali metal and halogen. So K is potassium, it's element 19, it has a +1 charge. Iodine is a halogen, it's element 53, it has a -1 charge. So to create the name for this compound, just simply take the potassium and add iodine to it, and then we change the ending for the iodine to IDE, showing that it's a negative charge. Here's another example, lithium and sulfur. So lithium, again, is an alkali metal, +1 charge, and sulfur is an oxide, it has a -2 charge, so there's 2 lithiums for every sulfur, but the name is pretty straightforward, just lithium sulfide. Here is sodium and nitrogen. Nitrogen becomes a nitride, so sodium nitride. Calcium and chlorine. Here calcium has a +2 charge, and chlorine, of course, is a halogen, calcium chloride. So metal ions with variable charge. Variable just means that you can have an element with different charges, and it depends on the conditions it's in. So let's take a cation. Again, it's just going to have the name of the element, but now we have to identify the charge using Roman numerals. So for example, if I have iron with a +3 charge on it, then I write out iron with Roman numeral 3. If I have lead with a +4 charge on it, then I have to write lead with the Roman numeral 4. So looking at our periodic table, there is a select group of elements that can have a variety of charges. Transition metals can have a variety of charges. There is a group of nonmetals that can also have a variety of charges, but we're only going to look at tin and lead. So Sn is tin and Pb is lead. And then there's the lanthanide and actinide series. Those also can have a variety of charges, but we're not going to, in this course, we're not going to spend a lot of time talking about these elements. Here is a table showing elements with a variety of charges. Once again, you could try to memorize this table, but I think it's going to be better for us to look at the periodic table and try to make connections with the element and the charge. Quickly going through Roman numerals because we're going to use these to identify our charge. The Roman numeral for 1 is just an uppercase I, and that's always going to be enclosed in parenthesis. 2 is going to be 2 I's, uppercase. 3, 3 I's. When we get to 5, use an uppercase V to identify 5. And then 4 is going to be an IV. So it's kind of like 5 minus 1 to give you 4. So the I comes first, and then it's 5 less the 1. So 6 is going to be VI. So the I follows the V. That means 6. 7 is VII. So it's like 5 plus 2. 8 is going to be 5 plus 3, so VIII. When we get to 10, it's an X, and so then 9 is going to be IX, and 11 would be XI. So it's a pretty simple system. So let's consider a simple example, and here we have iron with 3 chlorines attached to it. So the first thing you want to do, knowing that iron's a transition metal, is look at the anion. The anion here is chlorine. So each chlorine is going to have a -1 charge on it because chlorine is a halogen, and halogens typically have a negative charge. So I have a total of a -3. Because I have to have a neutrally charged compound, that means my iron has a +3. So I have iron 3 chloride. Notice the alternative would be iron with 2 chlorines. So again, chlorine has a -1 charge on it. So if I have 2 negative charges, I have to have 2 positive, and that would be on the iron. So it'd be iron 2 chloride. Very simple convention. The other thing that is important to point out here is that iron is only likely going to have a +2 state or a +3 state. It's not going to have a variety of other possible charges. Here's another example. Here's TiO2. So once again, I look at the periodic table, identify oxygen as in column 6A. So it has a -2 charge on it. There are 2 oxygens, and so 2 times the -2 gives me a -4. That means titanium has to be a +4. So I have titanium 4 oxide. And again, titanium typically comes in 2 possible states. So titanium 4 oxide, or I could have titanium 2 oxide. So that would just be TiO. So let's look at a couple other examples. And I always want you to refer to the periodic table to try to identify these compounds, because that's going to be the best way forward in doing this nomenclature. So here's CaBr2. Calcium is an alkali metal. It's element 20. And Br is bromine. That's element 35. That's a halogen. So the halogen has a -1 charge on it. The earth alkali has a +2 charge on it. They're defined charges for the elements, so they do not require a Roman numeral for the metal. And so we just call this calcium bromide. Another example, here's lead and chlorine. Chlorine we know has a -1 charge on it, but the lead is element 82. That can have a variety of charges on it. Most commonly it's going to have a +2 or a +4 charge on it. So since we have 4 chlorines with a -4 charge on it, the lead is going to be a +4. And because lead has the 2 possible charges, we have to use Roman numerals to designate the +4 charge. So lead 4 chloride. Here's nickel and sulfur. Nickel is a transition metal, element 28. Sulfur is an oxide. So sulfur is going to be a -2. Nickel, the transition metal, then has to be a +2. So I'm going to use the Roman numeral to identify nickel 2 sulfide.